Hi students, how you doing? We'll talk now about section 2.6, which is velocity and position by integration. From mathematics, we need to note that for f of x, we are talking math, not physics now in this part. For f of x, if we need to find f prime, we need to derive it with respect to x. And if we integrate, we need to know what is integration. If we need to integrate the f prime of x, it will give us f of x. And the limited integration from x1 to x2 will give us f of x2 minus f of x1. But most of times we have f of x1 is equal to 0. So we can find that f of x is equal to the integration of f of prime. This is f of prime. So the integration is the inverse operation of differentiation and vice versa. For example, we are just in math now. If we have f of x is equal to 3x cubed minus 2x, what is the differentiation of that function? D by dx to f of x is equal to d by dx to 3x cubed minus 2x, which is equal to 9x squared minus 2, which is f of prime of x. Now, what if we need to integrate f of prime of x with respect to x? It will be the integration. It is unlimited. It's open integration. There are no limits like in this way, like this integration. This is the f prime of x, 9x squared minus 2. When we need to integrate it, we need to raise the power of x and then divide over that numerical value, which is the new power of x, and we have the same coefficient, which is 9 minus 2 minus 2. We have x to 0. It is x to 0 here. If we add 1 to 0, it will be x to 1 over 1, which is x, plus c, which is the constant for the integration. In this case, we have 9 over 3, which is 3, x cubed negative or minus 2x plus c. If we have limited integration, then c we need it to be as 0. But this answer in general. Look at it, the same integration for limited values, which is the limited values are x initial and x final. We have in physics t initial, t final, x initial, x final, v initial, v final, and so on. It is easy operation in mathematics to know the differentiation and the integration. Now, again, in physics, now we will talk in physics. We have x is a function of t. If you remember that, we have 3 equations of motion. If we derive x with respect to t, it will be x dot, the rate of change in the position with respect to t. X dot, not x prime, it is x dot. If we derive with respect to x to the position, it will be f prime. But if we derive with respect to time, it will be dot. Okay? X dot, which is the first derivative of x, which is, it will be equal to v of t. It is the velocity or the speed as we talked before. What if we need to find the position with respect to t? If we integrate x dot with respect to t, which is the same as integration of velocity function of t with respect to t, it will give us again to the x of t function. So we can move between x and v as a function of t by differentiation or integration. And at we have two limits. We have t initial and t final. T initial it may be equal to t0. Sometimes it is equal to 0 seconds, and this is t1 or t2 or anything like that. So we have x final is equal to, if we integrate v of t, it will be equal to x final minus x initial as the properties of the integration. We need just to have, or to suppose that, or name x at t final. This one we can name it x, or x of t, and x at t initial, x naught, it may equal to 0. Now we need also to order this. We need to bring this term to here. It will be plus against the negative. So x final will be equal to x0 plus the integration from t1 to t2, or from t initial to t final, for the velocity or the speed with respect to time. T initial may be equal to 0. This is the relation between x and v, and x dot and v. What about the relation between v and the acceleration? It is the same. If we derive the velocity with respect to time, it will give us the acceleration. Also, we need to know also the relation between the acceleration and the position. We know that x dot is equal to v. V dot is equal to a, the acceleration. But v is x dot. We have another dot here. X double dot is equal to the acceleration, and x dot is equal to the velocity. The integration in mathematics is the area under the curve. So if we have v versus t graph, and we need to know what is x. X is x between t initial and t final. It is the area under that graph. And the acceleration is, as we see before, the acceleration is the slope at that point, at a point, okay? If we look at the acceleration graph with versus t, if we integrate from point t1 to t2 or t initial to t final, the area under that curve is the velocity. Okay? Be careful of that. This is the final idea. We have a relation between x, v, and a, the acceleration. All of them are functions of t. For example, if we have this function in x, if we derive it with respect to t, it will give us the function of velocity or the speed with respect to time. If we derive it again, it will give us the function of acceleration with respect of time. If we integrate that acceleration by integration, it will give us the speed. If we integrate the function of speed as here, it will give us the position function with respect to t. And note that the derivative is related to the delta x over delta t, for example, or the rate of change with respect to time, which relates to a slope of that function at a point or between 2 points or something like that. And the integration for a function is the area under the curve. So these two ideas are important. You will see these curves and this definition in the lab section. Now, let us look at this simple example. Okay, look here. If we have the acceleration as a function of time, 5, 15, t squared plus 3. The unit is meter per square second. It is acceleration. Okay? So 3 is acceleration. 15 t squared, all of it is acceleration. These terms, each term is acceleration. So the dimensionality should be verified. The time is always big or equal to 0 in seconds, okay? And we have initial values at t equal to 0. At initial time t equal to 0, we have the initial position is 5 meters and the initial velocity is 0 meter per second. Okay, we need to find the speed and the position or distance. Relations as a function of time. Okay, for the speed we need now to jump. We have the acceleration is given. We need to jump from acceleration to velocity, then from velocity to the position or the distance function. Okay, the first step, we are here, we need to move here. If we are at velocity, if we have the velocity function, then we can go by differentiation to the acceleration and by integration to the position function. Okay, velocity as a function of t is equal to v at t equals 0 or v naught plus the integration from 0 to t. The initial value of the integration is 0, the final value is t. We have a function. The integration for the acceleration as a function of t. Now the initial value of the velocity is 0, v naught is equal to 0. It is simple. Plus the integration of 15 t squared plus 3. The integration will be 15 multiplied by t cubed. We raised the power and divide over that numerical value, new 1, which is 3, plus 3t, because t here is t to 0. Then it will be t to 1 over 1. From 0 to t, we need to put t, then minus the magnitude of 0 velocity. So we put 5 t cubed, because 15 over 3 is 5, plus 3t minus, now we put 0, 5, 0 to 3, plus 3 multiplied by 0. This will be 0. So we have the velocity or speed. We don't know the direction, so we'll call it speed relation of time is equal to 5t cubed plus 3t. Now we can find the position. We need to integrate again. X of t is equal to x. It's the same relation, but we need to change x, v by x, and acceleration by v as a function of time. Integrate from 0 to t. But the initial position, it is at x at t equal to 0, x equal 5 meters. Then x naught is 5. The integration for the velocity function. Velocity function is 5t cubed plus 3t dt. And the integration from 0 to t. This is the resultant value for the integration. T cubed, it will be t to 4 over 4 plus 3t squared over 2. And we have the initial position 5 as is. So the final function x of t is equal to 5 plus 5 over 4t to the 4 plus 3 over 2t squared, and the 0 application here is 0. So this is the position function for our problem. Now if I give you any time, you can find x and v and so and a also. Look at this example or problem from paper page 62, which is 2.49. We have a rocket. We need to understand these questions. Start from rest. Rest means the initial velocity is 0 and moves upward in y direction. We can name it y, we can name it x, but we will take it as y. From the surface of the earth means at y equal to 0. We can take it as y equal to 0 for the first 10 seconds. So we have a period of time, we have acceleration function ay is given by ay is equal to 2.8 meters per second 3 multiplied by time. All of this term is acceleration. Okay? Now, where the positive direction for y is positive y direction, okay, is upward. What is the height? We need to find the y position of the rocket above the surface, above the 0 position of the earth at t equal to 10 seconds. We have the time at that time. We need to know the position function. What is the speed also at y equal at the when it is 325 meters above the surface of the earth. So we know the altitude of that rocket, but we don't know the time. We need the speed at that moment, okay? Now we have the acceleration function, which is 2.8 as given, meter per cubed second multiplied by t. We have here another function. We have here more simple function. And we have initial conditions, which is v naught is equal to 0 at t equal to 0, and y naught is equal also to 0. We have the position direction upward. We need to find the position at t equal to 10 seconds and the speed at y equal 325 meters upward. How much? Okay. By integration, we need to use integration. V of t is equal to v naught plus the integration of the acceleration with respect to t. V naught, we know it's 0 as given. Okay, the integration from 0 to t to 2.8 t dt. This will give us 2.8 t squared over 2 from 0 to t. The 0 term will be cancelled, will be go, okay, will not affect, and we have 2.8 over 2, it will 1.4 t squared. Then the speed function of t is equal to 1.4 t squared meter per second. Okay, what about the position? We need to integrate again because we are at this point. We know the acceleration. We need to integrate to go to the speed, then to integrate again to go to the position function. We need to go up by steps, by upper step by integration. Okay, now the velocity function, we need to integrate it, which is 1.4 t squared dt. The initial position y naught is equal to 0 plus the integration, the limits for that, just this term, not for this one, 1.4 t cubed over 3, the integration of t squared. This will give us 0, it will be 0, it will not appear here, plus 1.4 over 3 t cubed meters. This is the position function. Now let us find the required parts. Now we have y as a function of t is equal to 1.4 over 3 t cubed in meters. The speed function in y direction is equal to 1.4 t squared meters per second, and the acceleration function also in y direction is 2.8 t meter per square second. We can't find anything. We can find the velocity, the position, the acceleration at any time, at any point. Okay, so What is the altitude at t equal to 10? We just need to put 10 in the position function. It will be 1000 multiplied by 1.4, which is 1400 over 3. It will be 466.67 approximately meters in upward direction. What about the velocity at y equal 325 meter? What is t? We have v as a function of t, but not as a function of y. From y function, we can find t. We know y is equal to 325, which is equal to the function, which is 1.4 over 3 t cubed. Now, multiply by 3, divide over 1.4, will be equal to t cubed. It will be alone now. What is t? It is the square, not square root, it is the cubed root of this quantity, or this quantity to the third, okay? 1 over 3. This is the same as cubed square, root, I'm sorry. So t in this case is equal to 8.86 seconds. Now we can find the speed. We need to use this t in v or v function. We need to put 8.86 in v function. It will be equal 1.4 multiplied by this value squared as given. It will be equal 109.99, which is approximately 110 meters per second upward, because it is a positive value. Now this is another problem in the same page, which is 2.50. It is simple, just like the first example. You can do it, and I think this part or this section is very important to us in physics and in mathematics. Thank you.